in the previous lectures, we dealt with quite a lot of optimization techniques. So we discussed the optimization of constraint and unconstrained problems. So we discussed examples to use the techniques. And we also discussed the calculus of variation to solve the continuous time problem. So this technique requires quite a lot of computation. So I think some of you are working on the second assignment. So you know it requires a lot of computation to solve the method, to solve the problem. So a lot of combination of the solutions. So to reduce the burden, so one of the most popular techniques is to discretize the problem domain. So in this method, we want to discretize the problem domain. So here we want to discretize the problem domain. So we should not be confused with the discretization that we did before. So you remember in previous methods we ever discretized the cost function, we ever discretized the dynamic equations, but here are very different techniques. So in this technique, we try to discretize the problem space. So the idea is like this. So in a problem space, assume in a problem space, we got our starting point and we have our destination. So assume we got some obstacles at here. So the idea of this technique is to discretize the space into some grids, some nodes. So for example, we got some nodes, divided the space into some nodes or edge like this. So it's similar, the technique is somewhat similar to what you did in the GPS navigation. So remember, you discretize the space like this. So the whole space, the whole continuous space discretized into some grids and the edge, grids and nodes and edge. So for example, if you got some grids like this, so you can see there are different paths to go from the starting point eventually to the destination. But there are no nodes inside the obstacle, so that your vehicle will not go into the obstacle. So the idea is quite simple. So if we can discretize the space into these grids, then the coordinates of all these grids are known. You just think about your GPS navigation problem. So you got all the data for the roads. So all the waypoints, all the turning points are known, the coordinates are known. So if all the coordinates are known, then you can easily calculate the distance between these waypoints. So you got multiple choice to go from the starting point to the destination by using different routes. Then your navigator, one of the tasks of your navigator is to find the shortest path. So it's become another optimization problem. So you know all the distance between these waypoints. So you can easily determine the path with the shortest distance. So these are the idea and the topic that we want to discuss in this part. So it's a discrete path planning problem. And we also got another assignment in this part. So in the third assignment, you're going to deal with complex shape of the obstacles. So you can see this method is more flexible and more powerful to tackle any shape of obstacles. If you remember in our first assignment, we can only deal with the circular obstacle by using the potential function. But in this method, we can actually deal with obstacles with any shape, any particular shape can be dealt with. So you just discretize the space to the fine grades, then you're potentially able to find the shortest path. Then how to determine the shortest path is another optimization technique. So it's a technique that we want to discuss later. It's a dynamic programming techniques that are able to solve this set of questions. So the idea is to discretize the problem space. Then there are at least two problems. So the first problem is how to discretize the problem space. So how to discretize the problem space. So if we have a space like this, so how can we discretize the space into the set of nodes? So there are some other techniques. So the final problem in this area will be how to optimize. So the optimization technique. So at least we have these two problems to deal with, but in between, maybe there are some more problems in the practical scenario. So today we will address the first problem, how to discretize the problem space, how to discretize continuous problem space into a set of nodes and edge. So a key benefit by using this technique is that we can use the graph theory. You know, once you discretize the space, you got some kind of nodes. So this kind of nodes are well addressed in another big theory. So actually, it is known as the graph theory. So the graph theory is a very big area. So it's widely used in the mathematics and computer science to describe the interconnections between feasible states. You know, here we are only deal with two-dimensional space, but actually you can easily expand the graph into an n-dimensional space. So just think about if we have an n-dimensional space, then you've got different nodes in the n-dimensional space with coordinates, and we got a very complicated graph to describe all the interconnections between these nodes. To describe all the interconnections, all the distance between these nodes. So the problem could be very complicated. But the distance can be easily determined even in the n-dimensional space if your coordinates are known. So if the state of these points are known, then we can easily determine the distance and the location of these nodes in the n-dimensional space. So here we just deal with a simple two-dimensional space. So we use the graph to describe the physical connections between these waypoints, between these nodes of these waypoints spanning the operational environment. So we will not introduce in details the graph theory because it's too complicated to deal with. So we just try to use some simple function of the graph theory. So typically a graph can be represented by a matrix. So this matrix are represented by all the nodes. Also the vertices and the edges. So the vertices define all these nodes, and the edge define the connection between these nodes. And typically we use a matrix. So this matrix are known as the adjacency matrix. To represent the connection between the vertices. So for example, assume we have a simple graph, a very simple graph. We have 4 nodes like this. So we have 4 nodes. We have the first node, the second node, and the third node is the fourth node. So we have a simple graph to define the interconnection between these nodes, and we also define the distance between these nodes. So from node 1 to node 2, we assume the distance to be 4. From 1 to 3, the distance is 3. From the 2 to 3, the distance is 3. And from 2 to 4, the distance is 2. So assume we got this simple graph. So we can use a matrix to represent this graph. So this matrix is the vertices and the edges. Because here we got 4 nodes, we got 4 vertices, so we assume we can represent this graph with 4 by 4 matrix. So this 1, 2, 3, 4. This 1, 2, 3, 4. So from the node to itself, we just define this to be 0. From node 1 to node 2, we know the distance is 4. So this one is 4. From 1 to 3, the distance is 3. From 1 to 4, there's no connection. So the weight is 0, there's no connection. From 2 to 1, we got 4. From 2 to itself, we got 0. From 2 to 3, we got 3. From 2 to 4, we got 2. From 3 to 1, we got 3. From 3 to 2, we got 3. To itself, we got 0. 3 to 4, there's no connection, we got 0. From 4 to 1, we got 0. From 4 to 2, got 2. From 4 to 3, there's no connection, got 0. And 4 itself got 0. So we use this kind of matrix. We know the computer is very good. It's very good to deal with the matrix. So we can use this mapping to convert a graph into a matrix. In this matrix, we define the connection, or say the distance between each pair of the nodes. So this matrix is known as the adjacency matrix. So it's also known as the Laplacian. So all these are the terms that are widely used in the graph theory. So here we can see if we have a graph, then we can convert the graph into a matrix. And this matrix is in a position for the computer to process. But now the problem is how to discretize this continuous 2D space into this kind of graph. So a very popular technique to do that is the Voronoi diagram. So this technique is used to discretize the operational environment. So this Voronoi diagram is also a well-developed technique in the computer science, also in the graph theory. So this method is a partitioning of the space of a plane into regions. So based on the distance to some seeds. So typically we put some seeds in the space. So that usually the seeds are placed randomly. So typically we use some randomly placed seeds. So this technique will calculate the distance of all the points in the space, in the plane, to this seeds, and partition the space into the regions. So eventually, the region will contain the points with the closest. So for example, we place some seeds like here, So eventually this Voronoi diagram will be able to, for example, partition the space like this. So this partition is based on a criteria that all the points in this region, is closest to this seed. So it calculates the distance between these points with all the seeds and determine the distance to which seed is the closest. Then this will be partitioned into this region. So you can see the algorithm itself is actually quite complicated. But you don't need to implement the Voronoi by yourself because it's already well developed, and you can directly use the technique to partition the space, partition space. So if you put this random seeds, then you run the Voronoi diagram, it will partition the space into these regions. So these regions are known as the Voronoi cells. So these cells are known as the Voronoi cells. So this technique itself is quite practical. So we use an example to show the idea. So we are not supposed to do this by hand. So we use a MATLAB example to do this. So assume we have a space 300 meter by 300 meter. So assume we have a space like this. It's a 300 by 300. So to use the Voronoi diagram in MATLAB is quite easy. So you just randomly place the samples, place the points. It will partition the space. But to make it more interesting, we put an obstacle at here. So assume we got an obstacle. We got a circular obstacle. So it's at the position of 100 and 150 with the radius to be 50. So assume we got an obstacle at here, a circular obstacle at here.
Too stressed and die. Because
so the task is to participate the space, this whole space into the Voronoi cells. So we want to do something like this to participate this into the cells. But we are not going to enter this obstacle because eventually we want to avoid the rules inside the obstacle. So we are supposed to do something like this. It's quite random partition. So the idea is trying to do something like this. We want to divide the space into the discrete nodes. So these nodes are somewhat random, but depends on your seeds, depends on where you put your seeds. So once we divide the space into this discrete nodes, we can determine the distance from any point to another point. So for example, if you got your starting point at here, your destination at here, then you can determine the closest nodes to your starting point and your closest point to your destination. Then you can determine the potential routes to navigate through these nodes. So the MATLAB code for this one is also not very complicated, but I just go through the nodes to help you because we got an assignment for this one. So I just briefly go through some codes to help you to understand understand the code. But this assignment will require more programming skills than the previous two. So you require more knowledge of MATLAB and programming skills. But eventually, if you implement the method, the codes are not long. I think the total code will be within 100 lines. You can solve the problem. So firstly, we want to place the random seeds. So to place random seeds is very easy in MATLAB. So for example, we place the seeds, so we require the coordinates of the seeds. So I define the x coordinate. We just use the random function. So assume here we place 500 seeds. We place 500 seeds. So we use 500 and I generate a vector. So if you are not put a 1 here, you will generate a 500 by 500 matrix. So it's a 501 and multiply by, this rand function will give you the value between 0 and 1. 0 and 1. So in order to implement the range from 0 to 300, so we just multiply this one by 300. So this is because the range for this one is 0 to 1. So it multiplied by 300 will implement a value, random value between 0 and 300, and we generate 500 random values. So similarly we can generate the y coordinates. It's just the same idea. Same idea. So now if you plot this, you will get the random points. So we can just use a figure command. Then we plot the xn, yn, the coordinates, and assume we use a dot to represent all these points. Dot. So you can plot all these C's. So these are the command to create the 500 C's randomly distributed between 0 to 300. So next, we want to define this. We want to define this obstacle, because when we randomly place these points, so the points will be distributed all over the space, including inside the obstacle. So we want to remove the points inside the obstacle. So next, we define this obstacle. So how to define an obstacle? I think you're already quite familiar, because you define this obstacle in the first assignment. So to define an obstacle, we define the center, the x coordinate given by 100, and the y coordinate of the center is 150, and we define this radius to be 50. Then we use the polar coordinate to calculate all the coordinates on the circle. So I define a theta to be theta from 0 to 2 pi. Then from this definition, we can calculate all the points along the circle. So these are the equations that you learn in your middle school. So it's a radius multiplied by the cosine theta plus the center. So the y coordinate is given by the radius multiplied by sine theta plus the y coordinate of the center. So now we want to plot the obstacle onto the space. So you will require this simple command of hold on. Then you can plot this xc in terms of yc. Assume you use a red color and a solid line. So these are the command to define a circular obstacle. So now we have defined all the C's. Then we can use the Voronoi diagram to partition the space. Then this command is very, very important, but it's also quite straightforward to use. So this is the first section, this is the second section. So the third section is use the Voronoi diagram. So the Voronoi diagram, we will return something. So later I will explain what I return. And here, so we retain two matrices. So both are matrices. Return two matrices. Then the command is just the Voronoi. So the input to this command are the C's, the coordinates of C's. So remember, we generate the coordinates of the C's and here, xn and yn. So we just input with xn, with yn. So this will return all the coordinates. So this is the Voronoi diagram. So this command will partition the space into the discrete nodes, but including the space inside the obstacle. Because so far we have not dealt with anything. We have not done anything to remove the space inside the obstacle. So what I returned here, the first one is the x coordinate. So this one is the y coordinate, but it's not a single point. It includes all the edges defined here. So it could be thousand elements and here. But essentially, the Vx and Vy define the coordinates of all the edges. So remember, we divide the space like this, something like this. So for each edge, you got 2 points. You got the starting point, you got the ending point. So essentially, the Vx and Vy define all the coordinates are here, corresponding to all the edges. So next, we want to remove the points, or we want to remove the nodes inside the obstacle. So this part is actually quite simple in mathematics, and but to implement in MATLAB requires some simple trick to do that. So you will require this trick in your programming. So I just put Vx1 equal to the Vx, the first row in the Vx, So the Vx1 will be a vector. So this one is actually a vector, a long vector, maybe 1,000 elements, a long vector. So we have this Vy1 equal to Vy, the Vy1 is the first column in Vy. So this corresponding to 1 point, corresponding to either the starting point or the ending point in the edge. So next, if we want to evaluate whether the point is inside the obstacle or not, so we need to calculate the distance. We need to check the distance, whether the distance between this point and the center is smaller than the radius. If this one is smaller than the radius, then it's inside the obstacle. So we require to calculate all the distance. So I calculate this distance, but we know the distance requires some square root. So I just define the square, so we don't need to calculate the square root. So if the Vx1 minus the center, So remember, this one will be a vector because your Vx1 is a vector. The xc is a scalar. But this one will be vector. So to require to calculate the square value of this one, we require a dot square plus, so this x square plus y square will give you the distance. So the Vy1 minus yc dot square. So this actually calculates the square of the distance between all these points and your center of the circle. So we calculate the distance. So we want to find which distance is smaller than the radius and which one is larger than the distance. So in MATLAB, we have a very simple command to do this. So we can return the index. We can return the index in this vector. It's given by this find command. By this find command. So the condition of this find command is the square, this r square is smaller than the radius square, because we define the square of the distance. So this command will retain all the index inside the obstacle. So this actually return all the index of the nodes inside the obstacle. So this one is a simple trick in MATLAB to do this. So you can put any condition here that you want to satisfy, and you can use the simple command to find the index. So you can combine multiple conditions here. You know, in MATLAB, if you got multiple conditions, you may use the AND. You may use the AND or OR command to combine multiple conditions. So the next, we want to remove the nodes inside the obstacle. So to do that, firstly, we have this Vx new. So we just retain this Vx to put into a new variable. Then we have this Vx new with the index. So we have this index, and here, so we put this index into this command. So this index will represent the index in this matrix. So we know this matrix is supposed to be 2 by something, 2 by 10. So this 2 represents the x at here, because for each edge we only got 2 points. We only got one starting point and one ending point. So this one is supposed. So the first one is supposed to be the x. The first row of this matrix is supposed to be the x coordinate of the starting point. Then the second row is supposed to be the x coordinate of the ending point. So we only got 2 at here. But this one will be the index of the nodes inside this matrix. So we just set this one to be null. This will remove all the points. So similarly, we do this to Vy. Also set this to be null. So in this part, we want to remove. In this part, we want to remove the nodes inside the obstacle. So these are the commands to remove the nodes inside the obstacle. So next we can plot all the new nodes. So this is given by this Vx new, Vy new. So these are the matrix with all the nodes inside the obstacle removed. Assume we use a green color solid line. And finally, remember to set your display range to be 0 to 300 and 0 to 300, because the Voronoi will generate nodes outside this range. So these are the idea, I'll say the code. So it's not difficult to understand the code, right? So I can show you what happens in MATLAB with this code. So I already put the code at here. So firstly, I define this 500 random points between 0 and 300 for the x coordinate, for the y coordinate, and I generate a figure and I plot these points, plot all these points. So we run this code. We can see we generate 500 random points here. We just randomly distribute it, and we have not started to deal with the obstacle. So next we define this obstacle, so the center, the radius, we calculate the coordinates, and we plot this obstacle onto the on the space. And after that, we run the Voronoi diagram. We can see we plot this obstacle, and here we already got this Vx and Vy. We already run this Voronoi, so we can check the dimension for this Vx and Vy. So we can see the Vx is a 2 by 1483. So that means there are 1483 edges in this diagram. So we have 500 points. We have 500 random points, but there are supposed to be more edges to partition this space. So these are the x coordinate of the starting point and the ending point of the edge, and these are the y coordinates. So they're supposed to be the same dimension. So next, we calculate the distance between these points and the center of the circle, the center of the obstacle, and we find the index and the index. So this command will find the starting point. So this find the starting point, the distance between the starting point and the center. But we may also have another scenario that the ending points are inside the obstacle, so that we run the same command for the ending points for the second row of the Vx and the second row for the Vy. So this is supposed to be to check whether the ending points are inside the obstacle. So this one, the IDX1, supposed to be the index corresponding to the points, the starting points inside the obstacle. So this IDX2 supposed to be the index corresponding to the ending points inside the obstacle. Then we use this unit to combine these points. Then we set these points to be now. Then we plot this with a green color. So actually at here we can plot this Vx and the Vy. We can plot this. So I just show you the results. So before we remove the points inside the obstacle, so you know from the Voronoi diagram we return the Vx and the Vy. So actually here we can plot this to see what happens. You can see the Voronoi actually partitioned the space into the discrete regions. And you can see all the Voronoi cells are around this space based on particular criteria. So here we partition the space, the whole space, into the discrete regions. Also include the points inside the obstacle. So that's why we want to remove the points inside the obstacle. So to show the results again, so I just run the code from the start. So we have this random points. Because we place the point randomly, so each time you run the code, the points are supposed to be different. So next we plot this obstacle. Then here, if I run this code, we know we will remove the nodes inside the obstacle. So we will only show the Voronoi cells outside the obstacle. So let's see what happens. So we can see now because we already removed the Voronoi nodes inside the obstacle. So we only partition the space outside the obstacle. So I will place this code on the model, so you can try to run this code by yourself. But more importantly, for you to fully understand the idea behind the code. So the